Welcome to IR video number 3. So far we've covered the basics of infrared in video 1. We've covered the C to H peak, the O to H and the NH2 peaks right up the top between 3000 and 4000 wave number in video 2. And in video number 3 we're going to look at the carbonyl group. Okay, so we're going to look at this little doozy here and all of the molecules that contain it. So let's take a look at our spectra first. So we're going to start off with a very blank spectra here, and you'll see the first thing is that we have got at about 1700 wave number a very strong, sharp peak. And this is the peak that corresponds to our carbonyl group, our C double bond to O. Okay, so if we keep using our PLAT, our P-L-A-I-T, okay, we've got that here. So in this case, our P was our strong peak at around 1700, and that corresponded to a C double bond to O. So we need to analyze this now. This is a tricky one, so this has got its own video. There's a lot of compounds that have a C double bond to O, so let's take a look at some. Here's our C double bond to O. First of all, if it also has an OH, it's a carboxylic acid. If the carbonyl group has an NH2 also attached to it, that's an amide. If it has a Cl, we have an acyl chloride. If it is on the terminal, the end carbon, it's an aldehyde. If it is joined to an oxygen and another carbon chain, it's an ester. And if it's just a carbonyl group, but it's in the middle of the chain, it's a ketone. So what we have to do now is we have to combine information to figure out which one of these 6 groups that all contain a C double bond to O we actually have. So let's start with the alcohol. That's this one here. Okay, so what would we expect if this was an alcohol? As well as having the peak corresponding to a C double bond to O, what we would expect to see is a very big peak up here. Broad OH peak here. So if we saw that and that, we could say that we probably have a carboxylic acid. What about if we're looking for an amide? So I've picked these two because we already referred to them in video number 2. If this was an amide, it would have one peak for the C double bond to O here, but it would also need the NH2 peak, and remember that we saw that that was in a similar spot. It might be a bit smaller, and it's a doublet. So this is our NH2 here, right? So if we saw that and that, then we would have good evidence for it being an amide. Okay, let's go to the next one. What about this one here, an acyl chloride? Okay, we haven't been through this before, and actually the Cls and the Brs are a little bit tricky because they occur right down here in this fingerprint region. So what we're looking at for a acyl chloride is we are looking for the presence of a couple, 1 or 2, very sharp, medium-ish peaks at around 540 to 785, and this is our Cl. So the only thing we ever really look for down in the fingerprint region down here, right down here, are Cls and Brs. So if we saw these peaks as well as this peak for the C double bond to O, then we might have enough evidence to start suspecting an acyl chloride. Down here for the aldehyde, Let's take a different tack with the aldehyde and let's imagine what we wouldn't see if it was an aldehyde. Okay, so we've started off with the presence of this strong, it's a very strong sharp peak. We wouldn't see an OH peak, we wouldn't see an NH2 peak, we wouldn't look for a Cl peak, but we can use the absence of these two big peaks as evidence that this could be an aldehyde. The piece of evidence that we're really looking for with our aldehyde is this peak that we get for the C to H that we always get, that we don't usually talk about, usually has a lovely little shoulder peak. Oh, I've spelt that wrong. Sorry. Lovely little shoulder peak, which is this C. Actually, I've just drawn that wrong. Which is let's just call it an aldehyde C to H stretch. Aldehyde C to H stretch. Okay, so if we come back down here and look at the aldehyde, you can see there is a C to H here, but it's shifted a little bit because it's next to the C double bond to O. So instead of all the other C to H's which are in this peak here, this one is the C to H that's next to the carbonyl group. So if we have an aldehyde, we would expect this big peak here and this shoulder peak here of this C to H peak. Okay, let's carry on now for the ester. So the ester down here, what we're looking for in addition to the carbonyl peak for an ester is we are looking for at least one strong peak at around 1300. Okay, here's my 1300, and this will actually be a reasonably strong peak. Okay, so if we've got a strong, remember strong meaning long, sharpish peak at around 1300 to 1200, and we've got this carbonyl peak here, then we're looking at an ester. Okay, let me write ester in here. So ester, acyl chloride. This is our aldehyde in here. Okay, we're nearly there, and now we've got our ketone. Our ketone is characterized by the absence of any other peak. Okay, so it will not have the broad OH peak. It will not have the doublet NH2 peak. It will not have the shoulder peak on the side of this. It will not have this peak at around 12 to 1300 for the ester, and it will not have any obvious sharp peaks for the chloride. That is how we tell that something is a ketone. So when we come back up to our plat, if we have a strong sharp peak at 1700, and that's for our linked to our carbonyl group, we also have a strong peak at around 1250, and that is linked to our ester group CO, right? If we look down here, the ester group has a C or two C to O's. Then the analysis of this can involve linking these two together, but also linking to the absence of the OH, the NH2, the shoulder peak, and anything else we want to that we could reasonably expect to see on this. And then if we tie that all together, we might come up with the fact that this is possibly the spectra of an ester.